So, welcome to the 2024 Gothenburg International Science Festival. I'm Marnie Chesterton, I'm a BBC broadcaster, and I'm here adding a warm wave to the opening of the best and the only International Science Festival from Sweden, this year with the theme of waves. See what I've done there? So, part of the reason I asked you to clap was because the noise from your clapping is one such example. It's a pity we couldn't see it, but as each of you clapped, you created this sonic ballet of waves traveling from each of your set of hands to each of your set of ears through tiny molecules of air. Magic. Or rather, science. Science is the process of trying to understand the world around us. And the topic of waves, which was picked this year, is a really clever one to have chosen because you can approach it in so many different ways. So, waves describe the movement of energy or particles we cannot see. They also describe the stuff we can see. And I'm thinking, and Gothenburg residents will be thinking, about the water that surrounds us here. It also describes the movements, both human cultural movements and movements within science, those spurts of creativity and innovation within particular fields that yield new findings. And the recent death of physicist Peter Higgs makes me think of that really exciting, buzzy time when a wave of particle physicists descended on CERN as it prepared to switch on the Large Hadron Collider. But I'm getting ahead of myself. We've got plenty of time to talk science in a bit. First, the science is going to be with Nobel Prize winner Anne L'Huillier and festival speaker Stefan Helmreich. But first, a few words from people who made this festival happen. So may I, and I will attempt to not butcher the names, I'm so sorry. Jenny Borlund, Operations Manager of the Science Festival, Victoria Trygva-Dottier-Rolka, Deputy Mayor, and Anna Sostrom Duagi, Chair of the Board of Trustees and Vice President, Strategic Innovations at the Nobel Foundation. Please all, welcome, welcome. Is there a mic between you? Is this one? Right, Anna, you first. So, do we really need a science festival?
Well, yes, of course we do. Just look at this wonderful audience here today. I think that's the testament that we really need this festival. And as you say, it's not only the only international science festival in Sweden. It's actually one of the biggest science festivals in Europe, and I would say the world. I would say that it's actually one of the best science festivals in the world because the team behind this festival, they have an enormous know-how on how to create a fantastic program that reaches all of us, from kids, people like me, students, teachers, everyone. So you just have to go in and look at the program with over 200 activities reaching out to everyone. And this is almost a 30-year celebration of this festival. And I just want to say that I think that in this world we are living in, it's increasingly complex and difficult to grasp and understand. We really need to constantly educate ourselves. And all of us need to do that in order to understand the world and also to participate in the discussion and dialogue as citizens and participate in a democracy to be able to select and vote for the leaders that we want. So I think everyone should take the opportunity to really enjoy this week, go to all these fantastic programs and participate in the dialogue. Also in the time where a lot of in-person meetings happens online, I think we need these real meetings where you can actually meet a Nobel laureate, you can meet a scientist, you can meet this fantastic crew behind this. So take that opportunity and be happy that you live in Gothenburg.
Well, Victoria, as well as being Deputy Mayor, you are also Chair of the Gothenburg School Board. So can I ask you about the school aspect of the festival? Because for the general public, there are events until Sunday, I believe, but the lucky schools have a whole 11 days of programming. Why is that important?
First of all, thank you. Of course, we are happy to live in Gothenburg, and this is a wonderful festival that we are extremely proud to take part in and that we've done together for many, many, many years. And yeah, to why it's important for the children and the schools to be able to have this wonderful program. I know my kids, I have 5 of them at home, and they're participating in many, many different aspects of this week. And I would say in this world where our children happen to have the most anxiety about environmental changes, poverty and world health and all the complex problems that we have, to engage in these different tasks with curiosity and happiness and just to have fun memories, and also to help them make informed choices with the phones and with all the media completely and always distracting them. I think that it's never been as important as now to engage in this.
And is that something that applies to the rest of Gothenburg and Sweden, or is this, what does this festival mean for the city?
I would say it means a lot, and to us as a nation, where we want to be a nation that competes with knowledge and science and also stands out in the world with good solutions to the great problems that we have together. I would say it's absolutely, we have to keep on going. But I want this to be larger than 1 week. I want this to be, I want us to be a scientist vetenskapsfestival all year around, to have this work between the public, between the universities, between me as officials and the schools, and to have this collaboration also with our companies and to work all year around.
There's Jenny, who is one of the organisers of the festival. So, can you do this all year round? Christmas every day?
Of course we can. Everything's possible.
Who made this festival possible?
Well, first of all, I would like to say that the festival wouldn't be possible without you in the audience, all the visitors, all the schools around Sweden that participate, and of course all the scientists and researchers and everyone participating in the program. So without them, no science festival. But of course we have a few really important partners and our board of trustees. So I'm wondering if I can have a little slide and show it. We have our board of trustees are the Gothenburg University, Chalmers University of Technology, Swedish Research Council, West Sweden region, the city of Gothenburg, of course, and then have I missed something?
Well, they're all
yes, Göteborg and Co. Trade and Industry Group. And look at this lineup. I mean, look at those. These are all companies, foundations that all believe in knowledge, education, and in an inclusive way for the future. So, yeah, we're really happy to have all of these partners behind us so we can make this as accessible as possible. Yeah, but then, to be here today is because of the Stena Foundation for Research and Culture. And that is quite amazing, I have to say. For several years, we've been able to open up for anyone who wants to come and listen to really clever people that are like top scientists in the world. We have had Jennifer Doudna, Nobel Prize winner. We have had Richard Dawkins, Max Tegmark. Lots of interesting names. And today, Anne Lullier and Stefan. So, yeah, thank you so much, Stena, for Stena Foundation for doing this for us. Thank you so much.
Thank you. Thank you, Jenny, Victoria, and Anna. And if anyone's interested in getting a little taster of the type of programming at the festival, in the foyer afterwards, there's something called Soapbox Science, which is women in science getting on a soapbox and talking engagingly about what they do and why it matters. And talking of women in science, let's move along to our main speaker, Anne Lullier, Nobel laureate. So, oh, yes, do come up.
Electron, I loves you.
I should say that Anne personally chose that music. So Anne is a professor of atomic physics at Lund University and shared the 2023 Nobel Prize for Physics for her experiments on attosecond physics. So that's the shortest amount of time that we currently can distinguish. By creating a new window in time, the fastest ever shutter speed, to use a camera analogy, Anne has allowed us to get snapshots of things we've never been able to see before. The field of attochemistry was created as a result of her experimental, theoretical, and groundbreaking research. And through that, we're expecting breakthroughs in the future. So, I'm handing over to this evening's keynote speaker. Put your hands together again, Professor Anne Lullier.
Thank you very much. Can you hear me? No? Hello? Is it better? No? It's a bit better. Yeah. Okay. So I'm going to tell you about the Nobel Prize in Physics 2023. And it's a lot about waves. We are working with light. These are waves. And we look at electrons. These are both particle and waves. And actually mostly waves, as you will see. So I will start by showing an arrow of time, just to show you that these are very, very, very short time scales. So we start here by the age of the universe, 13.8 billion years. You have a few astronomical times, the year, the day. This is the history of humanity. And then you have 1 second. This is time for heartbeat. You have millisecond. This is mechanical times. Then time for electronics. This is nanosecond, 1 billionth of a second. And then I'm going to discuss in more detail the time of motion of atoms in molecules. It's femtosecond. Time for motion of electron in atoms, attoseconds. So in general, the lighter the particles, the faster they move. Here you have a molecule, and the atoms in a molecule, they are not static, they really move. They move very fast. And to capture their motion, one needs to have very, very short flashes of light, laser light, femtosecond laser light. And this led to Nobel Prize in Chemistry in 1999 to Ahmed Ziwal. Let's go to atoms. This is a picture of an atom with a nucleus and electrons that rotate around the nucleus. And now to capture the motion of electrons in atoms, we need attosecond pulses. So 1 attosecond is 10 to minus 18 seconds. Very, very short time. And this has led to a Nobel Prize in Physics last year. And here you have a picture of the announcement of the Nobel Prize at the Royal Swedish Academy of Sciences to Pierre Agostini, Ferencvaros, and myself. And here is the motivation for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. So how did the whole thing start? It actually started 37 years ago, so it's really a long time. This is very basic research. It simply takes time. And it started in 1987 when we decided to look at the light that was emitted from atoms when they are exposed to laser light, intense laser light. So this is some kind of experimental setup, very simple. And what we did was to look at light emitted using a grating. If you don't know what is a grating, you can think of a prism. So some optical components to analyze the light, to send the different colors, the different frequencies of the light into different directions, and then you have a detector. The idea behind this experiment was to look at actually the fluorescence from the atoms excited by the laser light. This was the aim of the experiment. This is not what we observed, and this was really a discovery. We observed instead high-order harmonics of the laser light. As you can see on a spectrum here, you see many peaks, which correspond to a multiple of the laser frequency. For example, 25 here, this is the peak, the first peak that you see here. This means that this light has a frequency equal to 25 times the laser frequency. I'm sure you have heard about harmonics before, maybe not in connection with light, but in connection with music, with the sound. And actually, it's very similar. This is the spectrum that you obtain when you play the violin. Actually, it's alto violin. When you play the tone A, you get, of course, the tone A, but not only this tone, but actually several harmonics of this tone. And that means that here you have 2 times 440 hertz, this is the frequency, 3 times, 4 times, etc. And it's the number of harmonics that actually make the clang of a music instrument. It's very different for different music instruments. So there is really an analogy here. In both cases, we have a strong interaction here between the violin and the stroke, and here between the atoms and the laser. And in both cases, you produce high-order harmonics. Now, if you let's look at the electromagnetic spectrum, going from radio waves, and now I'm really talking about waves, to talk about light. So here we have the radio wave with a long wavelength, and infrared, this is the visible spectrum, which is only a small part of the electromagnetic spectrum, and then you go to ultraviolet, X-rays, gamma rays. So now if you start from actually the infrared, this is the wavelength of our lasers, often. So you could start with a certain frequency f here somewhere, and then you multiply it by an integer, and this integer can be quite high. Then you end up here. So this is a little bit higher than the ultraviolet light. It's a little bit below X-rays. It's called XUV, extreme ultraviolet, or it can be labeled XUV or EUV, depending on your field. So this radiation is invisible to the eye, and it's actually absorbed by air or by matter. So to study it, we need to work in vacuum. We work with vacuum chambers, and where we get rid of air. Now, what about attosecond pulses? What is the connection? So now let me show you some waves and try to explain the relation. So here I'm plotting 3 harmonics. These are waves with a certain frequency. So slightly different frequencies. Here I'm taking harmonic 17, 19, and 21. And let's assume, this is an hypothesis, let's assume that these harmonics, the maxima of these harmonics happen to coincide at a certain time, okay? For example, here. Because of the periodicity of the process, this will repeat itself a little bit later. Here you have, again, the maxima at the same position. Here you have the minima at the same position, and then again the minima at the same position. You follow me? Yes? So now let's sum these waves, okay? We can do that with the head. So these waves, they go plus and minus, and then we sum these 3 waves. What do we get? Okay? We get, when they are synchronized, when they happen to be at maxima at the same position, then you will have a maximum here. Okay? In the middle, the maxima and minima happen at different time, so the total will be approximately 0. This region is called, you have constructive interferences between the waves, and in between you have destructive interferences. And again, here you will have light, no light, light, no light. So this way, we concentrate light under very, very short time interval. If I plot, this is the electric field of the light. If I plot the envelope of the electric field, and actually the intensity of the light, I will get something like this, a sequence. We call it a train of short light pulses. And this was really exciting. Oh, can these high-order harmonics lead to very, very short light pulse, a new time scale that no one had produced before? Now you can also understand, if you follow this picture, that if I am summing not 3 harmonics, but let's say 10 harmonics or 20, and if they are all synchronized at a certain time, then I will get even shorter pulse, right? So if you have 10 harmonics, you can get even shorter pulse of the order of 100 attosecond. And here I'm illustrating another very well-known principle in physics called Heisenberg principle. If you have many harmonics, which means a broad bandwidth, many frequencies, a large frequency bandwidth, I can get very, very short light pulse. Uncertainty in frequency, certainty in time. This is Heisenberg principle. So, is it true? And the answer was given by actually a deeper understanding of the physics behind the emission of high-order harmonics or the emission of attosecond pulses of light. So now I'm doing a little bit of quantum mechanics, which explained, this was discovered in 1993 by theorists and really gave a very intuitive picture of this phenomenon. So here what is represented is actually an atomic potential, it looks like that, with an electron which is bound in the potential. So now we have a strong laser field, and this laser is going to bend this atomic potential in one direction. And this is why it looks like this. It's not like this anymore, it's like this because of the laser field. So here you have a high wall, but here you have a barrier. Okay. Now, the electron can go through this barrier. This is very strange phenomena that you have in quantum mechanics. In classical mechanics, the electron will still stay in this potential group, this potential wave, but now this is quantum mechanics. There is a certain probability that the electron goes through this barrier. This is called tunnel ionization. Then the electron is driven away by the laser field. The laser field change of sign, it's a wave, change of sign. The electron is pushed back towards the atom, and there is a certain probability for the electron to come back, to recombine. And in this process, there is emission of light during a short time attosecond pulse. So if this sounds now very tough to understand, I have an analogy, okay? And since we are in Gothenburg, I'm going to talk about Liseberg, okay? And this is called the adventure of an electron in a laser field. This, in addition, it's in Swedish, so, but anyway. So here you have an electron which is bound to an atom. It's a strong force, and it's good because otherwise we would not exist. So that's good. But you have a strong laser on the side, and you can represent this way, an electron in prison. And here there is Liseberg and roller coaster. And so the electron would like to go out. What does he do? Now I see if you have listened. What does the electron do? Yes, he tunnels. Or she tunnels, I don't know. Yes, this is the process of tunnel ionization. So, yes, the electron is out, and he has fun, and he's going up and down in this laser field. Everything is fine. Unfortunately, this adventure is finishing bad. The electron just happened to be on to meet the ion left, and the prison, which is open. So he falls into this prison, and the energy in this adventure is transferred or is given as a scream. Okay, in the physics I'm trying to explain, it's a light pulse. This is the end of the adventure. Yeah. So I want to say one more thing about these pulses. So just to summarize, we have short pulses. The theory I just has presented in a form of a small story says that this synchronization of the high harmonics is more or less true, and that indeed we have a series of very short light pulses. Now, this light is not incoherent, as is on this picture. Most of the light that you have in nature is like this. You have excited atoms that send out light by fluorescence, and so they send out some waves in any direction and any time. So there is no phase relationship between these different waves, and this is the light from these lamps, from the sun. So everywhere the light is like this, except laser light. So laser light is something like this. All the atoms in a laser medium send waves in one direction and in a coherent way, which means that all the waves are add together, are in phase. And the harmonics that we produce, the attosecond pulse, this is laser-like radiation, where you have this synchronization now of all the atoms in the medium. You can also see that as a gigantic orchestra, which is led by a conductor. And here I'm just drawing like 12 atoms, but in reality you have billions of atoms in this medium that produce light, which is acting together like a giant wave. I would like to give you a little bit of picture how these experiments are done and what kind of equipment we need. And also, at the same time, maybe I go back to my personal history. I am French. The first experiments in this field were done in Saclay, a research institute in France. But actually, I was in Chalmers as a postdoc in 1986. But then in 1992, there was the beginning of European collaboration, a little bit pushed by the European Union. And I started talking to some Swedish scientists, and in Lund, they had, so let me show you some picture. So this is a picture of the three scientists in Lund. They had constructed a laser facility in Lund with a state-of-the-art laser system that you can see here, called terawatt laser, based on a new laser medium called titanium sapphire. And this is a picture of myself a long time ago. And my first PhD student. Actually, we were building a dedicated instrument to study high-order harmonic generation. So here you have, this is where the gas is being brought. So here you have your gas medium. So you have chambers where you evacuate. So this is vacuum chamber. So inside here you have some optics to analyze the radiation, and then you have a detection here. So we were building this dedicated instrument. So we were invited to Lund to study these processes using this fantastic new laser, state-of-the-art. So this is why I came in Lund in '92. Now the reason I stayed in Lund, or actually came back to Lund, is a different story related to a certain person here. So what do we do with this slide? We are trying to follow this. As I said at the beginning, this is the time scale of electron motions in atoms and molecules. So what can we do? I'm starting here by, again, this picture that you have seen at the beginning, which is a little bit wrong. This is actually Bohr's atom model. But when you work with this model, you realize that the time scale for an electron here to rotate around the nucleus in the simplest case, called 1s electron, is 150 attosecond. So you see, this is the right time scale. However, if you think about this type of picture, it's a little bit wrong to think about a small ball doing like this. It's actually a wave. And the only thing you can, and the probability actually to find the electron somewhere on the trajectory is the same. So there is nothing you can follow like that. However, there is something we can look at. It's another well-known effect called the photoelectric effect, which was explained by Albert Einstein in 1905, where this consists in the simplest system, an atom. You ionize an atom by sending some radiation with high photon energy, and you get an electron. So photoionization, very simple. You send a photon, and you emit an electron. So the question, this process had been considered as instantaneous before, but now, thanks to this attosecond pulse, we can really follow and measure this time necessary for the emission of electrons. So I'm going to show you, to illustrate that a little bit, and to show you what we can do with our techniques and the kind of movie that we can do. So it's a little bit, we use this attosecond pulse a little bit like flashes of a camera or ultra-fast camera to follow a motion. So here I'm going to show you, this is photoionization. So again, forget this particle going away. It's more like a wave. As you see here, in this case, the electron can be emitted in this direction or in this direction, this direction, this direction, not so much along this perpendicular direction. Okay, so this represents the probability for the electron to be emitted somewhere. Okay, so it's really like a wave, like a water wave. So now I'm going to, with help of a laser, we are going to perturb this wave, to move this wave this way or this way, and then try to follow the motion. And this is what we did here. So this is really results from an experiment where we try to wobble these waves and see the motion. So this was one of the first demonstration of the use of these techniques to really follow the motion of electrons. So I'm almost done with this presentation. I'm going to present an application which is a bit different because people now ask me all the time, oh, why is it good for? And yes, you laugh. So I give two answers. The one answer is that this is still extremely basic research. It will be useful for society to follow this motion maybe in 50 years from now. Maybe I exaggerate a little bit, but maybe 10, 20 years for now. This will be useful when we start to follow electron motion in more complex systems, like big molecules, like condensed matter, when we can really see the beginning of a chemical reaction, and if we can see, we can also maybe control a little bit. So that's a little bit the vision of this field of research. But again, we are not yet there. But there is one thing which is happening now, which already in the industry, and I feel that it's very exciting. It's not so much about using this time scale, but using the fact that we have radiation with a very broad bandwidth, so many frequencies. Now I'm going back to the high harmonics, many frequencies in this EUV or XUV frequency region. And the application is actually for future computers or telephones or whatever. It's to do metrology of very small integrated circuits, the next generation integrated circuits, reaching dimension of the order of 10 nanometer, and actually also with a certain, now they print this processor on a wafer, not only in 2 dimensions, but also in 3 dimensions. They put transistors on top of each other. And it turns out that this radiation, high order harmonics, is really useful to look at these very small circuits, and in particular the depth information is what can be detected using these sources. So this is already in the end of the industry. It's not yet in your pockets, right? But maybe in a few years from now, who knows? So with that, I would like to thank you very much. I would like to thank this research is not done by a simple person. It's done by a group. As you see here, they are celebrating here something that happened on the 10th of December. Of course, I want to thank the organization that found this research. And I would like to thank a few groups in Gothenburg with whom I have been working with. First of all, I was doing my postdoc in 1986 together with Joran van Ding. It was a very important time for me and very, very nice. If you want to see harmonics and attosecond pulses in Gothenburg, there is something called the Atto-hallen at Göteborg University, and we have a very nice collaboration with Raymond Feifel and Richard Quib. And we are also part of the VACT Center, which is led by Per Delsin in collaboration with Anton Friis Kokum. So thank you for your attention.
Thank you, Anne. And stay with us because we've got more wave chat coming up. So we've got a bit of time for a discussion, and joining us to talk about other kinds of waves is Stefan Helmreich, and he's a professor of cultural anthropology at MIT. Also the author of Alien Ocean, Sounding the Limits of Life, and a book of waves. So he specializes in the anthropology of scientists, specifically oceanographers. So let's give a warm welcome via some sound waves. You get what I'm going, it's clapping, for Stefan.
Rewrite it, plug it, play it, burn it, rip it, drag it, drop it, zip unzip it, lock it, fill it, curl it, find it, view it, code it, jump and lock it, surf it, scroll it, pose it, click it, cross it, crack it, switch it.
Okay, I'll go in the middle. Stefan, you're going to be back here, same time, same place, well, 5 o'clock, right, tomorrow?
That's right.
As part of the festival programming. So waves, as we've established, are very much the theme for this year's International Festival. And we've just heard how, Anne, your laser light waves give us invaluable basic information. But other waves in the form of, I don't know, different forms can predict things like geological events, they can predict sea level rise, geopolitical news. This is the point where it's going to feel a little bit like the film Inception, because Anne studies with the waves, Anne studies the waves, Stefan studies the scientists who study the waves, right?
That's exactly right.
So in his book on waves, he covers mythology, surf culture, feminist and queer theory, film, indigenous Pacific activisms, Black Atlantic history, and cosmology. Have I missed any out? Oh, LIGO, gravitational waves.
That's right, yeah.
So I feel like between the two of you, we've pretty much got waves covered. Stefan, what drew you to writing a book of waves?
Well, I'm fascinated by waves because they're both things in the world as well as patterns that propagate through things in the world. In other words, they're both ephemeral and material. So to take an ocean wave, for example, there it is. And yet understanding that that's what you're seeing requires a lot of conceptual kind of pattern recognition work. And so I was drawn to the way that scientists try to grapple with this kind of thing that's simultaneously ephemeral and material, and the way that they do that through, for the cases that I was thinking about, for oceanographers, the way that they do that through field work by going out to sea, the way they do that in laboratories by making scale models of waves, the way that they do that in computer simulations. And I'm really interested too, you mentioned all these different kinds of waves, I'm interested in all of the analogies and metaphors that exchange back and forth between different kinds of waves. So,
well, I was interested in analogy in your work because we were talking before. Is this a clock that you've invented? Is it a microscope? And you said no. It's most like a camera. Yeah. So I've seen the analogy of someone trying to take a good picture of a hummingbird flapping its wings, and if you don't have a smart enough camera with a fast enough aperture, you're going to get a blur, right?
Yeah.
And
I mean, yeah. This is, of course, a way to explain what we are doing, like an analogy with an ultra-fast camera. But in reality, we are measuring waves. So it's not exactly what we're doing. We are actually measuring. Now I'm going a little bit more technical. We are measuring electron waves, and what we measure. Normally, you can measure the energy of electrons, but what we can do with our techniques is actually measure the position of the maxima and minima of our wave. So we measure what is called the phase of the wave. This is what we're doing. So this is very much wave measurements.
And for that, you need the shortest snapshot that is possible.
Yeah.
A billionth of a second.
Yeah. Or a few tenths.
So there are more attoseconds in a single second than there are seconds since the beginning of the universe.
Yeah, that's the scale, yes.
When you tell people that, do they have trouble grasping that?
Yes, I do too, actually. So I simply say it's incredibly short time.
And your co-laureate, Ferenc Krauss, said that you've developed this way of looking at nature in a new way. And he says that's wonderful. He feels it to be a superpower. Do you feel you've created a superpower?
No. I think this is research. This is very fundamental research, and we are progressing peu à peu. If I am. Takes a long time, but it opens doors, and I would like to say it opens unexpected doors. And just to take example, when we discovered these high-order harmonics was completely unexpected, what we found. So this was really, this is not what we were looking for. We were looking for something else, and this is what we saw. Another example is this application that I mentioned at the end for next generation integrated circuits, for next generation computers, and this was totally unexpected, and it came about just a few years ago.
Okay.
So this is the beauty of research.
But that was 14 years ago, right?
No, 14. No. There was the discovery of high-order harmonics is 37 years ago. The application I mentioned, it's the first idea is like 7-8 years ago, so it's very recent. And the use of attosecond pulse to try to look at electrons, this is like 15-20 years old. This is just the beginning. This is what I'm saying. It will take time to really find new things, and that would lead to application for society.
There are some really interesting overlaps between looking at really fast snapshots and looking at really fast snapshots that oceanographers do. And I want you to tell me about a piece of equipment that oceanographers use that you got to visit. So you saw Anne's picture of the experiment that she built in a lab, and you've got this sense of, okay, there is a lab, and we build these things within it. FLIP is different to that.
So FLIP is an oceanographic vessel, which it's an acronym which stands for Floating Laboratory Instrument Platform. And what it is an oceanographic craft that heads out to sea, kind of like a regular ship, but once it gets to where it wants to go, it rotates by 90 degrees, and everything inside is on swivels. And so, you've got sinks in both directions, you've got tables in both directions, and the idea is that by going out to sea and flipping into this upright position, you can kind of attenuate the wave action of the ambient seawater around you, and turn what is essentially kind of the field into kind of a laboratory setting. And you can use it as a platform from which to do things like try to figure out how fast the waves are going around the ambient water near the flip ship, which is what people call it.
And so about 9/10 of this ship disappear under the water.
That's right. And it is kind of like an MC Escher kind of experience. So
Because you need to create people's work and living spaces that works
both directions.
when it's that way round and also when it's turned that way round.
That's right.
So extraordinary place to visit, to see. What experiments were you seeing?
I was seeing people doing attempts to kind of take these very fast snapshots of waves as they broke on the surface. So they would sort of flash a laser in the order of several microseconds and produce kind of a movie. So there's kind of some similarities with the attosecond work, that part of what the oceanographers are doing in the attempt to capture what waves are up to is to create a kind of cinema. And I became really interested in that also as a kind of analogy. And
how is that different to just me getting my phone out and phoning, taking a picture of the waves as they break on the shore?
Well, it's a strobing effect that you can't get in the same way, right? And also what they're interested in is the aerosols that go above the waves. As the waves kind of crash, they produce all of this kind of spray. And they can do this very, very fine-grained kind of location of where all of the particles are and try to learn something about why it is that waves break in the open ocean. And one thing I was surprised to learn is that scientists don't actually know why waves break in the open ocean. They know that they do. They can predict when they will do that. But the mechanism is itself still something that's very much under investigation. And these kinds of very fast snapshots are part of the key to solving that puzzle.
I wonder whether you're done with waves now. I mean, you've written the book. Do you see them everywhere now?
Of course they're everywhere. And yeah, I mean, I think, as you mentioned, the book includes things like waves in folklore, waves in histories of social movements. Certainly, we've just been through a pandemic, which was modeled as a wave. And the very early history of understanding pandemics as unfolding in waves happens when people start making graphs that kind of look wavy-like. And that's sort of a metaphor, but then people start to make mathematical models. And in the early 20th century, you start to get the idea that you could intervene and flatten the curve as a kind of result of that kind of modeling. So I was finishing up this book during the COVID pandemic, and so it was this kind of uncanny thing to see the waves kind of at every scale that I could sort of access.
Excuse me, can you look out? Because
Okay.
I can't see your lips.
Okay.
Yes, don't look at me, look at them. So that must have been really hard, that you're writing a book during the pandemic, and then science keeps happening, and you keep thinking, well, this is about waves as well. Should I add another chapter?
It's true. And in fact, one of the things that happened at the end of when I was writing this book was that some people in Southern California became worried that COVID-19 might aerosolize over the waves. And so a lot of the people who were investigating aerosolization over waves started to kind of ask the question of, are there disease vectors that can also be traveling over the waves? It turns out that it's not nearly that simple, but people went from studying ocean waves to studying COVID waves, and that was a really unexpected thing that happened as I was finishing up the book. So it's not just the modeling of the waves through graphs, but also through the very physical substance of what waves can do and be.
I discovered during COVID that science is hampered in some ways by the fact that it's siloed. So I talked to aerosol scientists trying to find out whether COVID is airborne. And you talk to the aerosol scientists who study tiny
right.
bits that big, and then you talk to the droplet scientists who study slightly larger but also tiny droplets. Mm-hmm. They didn't really talk to each other prior to COVID.
Right. I mean, one thing that's interesting about ocean wave scientists is ocean wave science has been dominated mostly in the 20th century by physicists. But we all know that waves are made of things as well. They're made of water, They're made of maybe chemical pollutants. And so in recent years, there have been chemical oceanographers studying, strobing. Chemical oceanographers studying the aerosolization of wave. There have been biological oceanographers studying the multicellular organisms that exist within, or the single-cell organisms that exist when waves crash. When waves crash, it's not just water. It can be biological things as well. And so one thing that really surprised me was that this field that had been dominated by physicists was starting to see chemists and starting to see biologists also all participating in trying to understand what waves are and might afford.
Now, my physics friends would say that's because all science comes down to physics. Is there one discipline that gets to claim waves as theirs?
Say again?
Is there one discipline that gets to claim waves as theirs?
Well, the physicists have done a good job of it. But if you want to understand the making of ecologies in coastal environments, for example, if you want to know how red tides happen or dinoflagellate blooms, you need the biologists to also participate. And they need the physicists. They need the physicists to understand, how the ecologies are kind of accordioning back and forth to produce these different kinds of niches within which organisms might exist.
Is there any way where the film theorists come in here? I mean, is there anything they can learn from the scientists or vice versa?
Well, actually, one of the things that scientists do when they study waves is they make scale model waves in laboratories. And now a scale model wave unfolds in a really peculiar way from a temporal point of view because you can't scale down the water molecule. And so in order to produce a scale model, you have to do a lot of complicated math. And the people who do that actually take a page from science, from special effects, as they try to understand what it is that they're seeing unfolding in their physical wave tanks. They say, well, we have to do this kind of equation to sort of slow things down by this much and the inverse of this and so on. And it has a lot in common with what we've come to know and love in special effects films. And in fact, one of the chapters in the book is all about very large waves in movies. And until the rise of computer graphics, waves in movies were very unconvincing because you couldn't scale people and a model of a wave kind of in a convincing way to make it feel as though they were kind of in the same world. But now with computer graphics, you have all of these complicated mathematics being employed to generate
a better disaster movie.
That's the phrase I was looking for. Thank you.
And thanks to your research, we can understand more about what is happening within atoms. You've mentioned one use for that. Are there any others? Is it still, I know you're saying, this is really basic research, we're at that stage.
No, but our field is a little bit going into many directions at the moment, and towards chemistry, even biology a little bit, condensed matter, physics, industry, and a little bit quantum physics as well. So this is what is happening. It's still, with some exception, still very basic, but it's really, now these tools are going to be used in different areas.
And is there anything beyond the attosecond?
Yes, the next scale is called zeptosecond. So this is 10 to minus 21. You can, so sometimes I have this question, can we go below 1 attosecond in this zeptosecond range? So this is what I explained during my talk. To go to zeptosecond, you need to have very, very broad bandwidths, many, many frequency. This is again Heisenberg principle. So can we have enough bandwidths? Well, through these processes, in some condition, you can actually have a very large bandwidth, which would allow us to go to zeptosecond. But now the difficulty is to make all of these frequencies be together at the same time. So this is not solved yet. So it's a bit, it's not the fundamental limit, it's more maybe technological limit, but this is not solved yet.
Is that in your future as something that you want to solve?
Not really, because I think in our research now we would like to use this radiation. So this is the first goal, is to really use them. I mean, we're not chasing records. Of course, it's fun, but so we are not really. But probably some people are trying to get even shorter pulses, of course.
And can I ask, you've won a Nobel Prize. How heavy is it? Also, is it made of gold?
I mean, the prize actually is many things. It's a medal. Mm-hmm. It's a diploma, which is very thing. We send some art, some painting, which is very thing. There's some money, and of course the honor. It's the biggest thing, I think. This is maybe the heaviest one. Is the what you expected to do.
And you know, do you put it on a pendant or?
No. It's heavy. It's heavy.
I did ask her earlier. I was like, "Where do you keep it?" And Anne went, "I'm not telling you." So Nobel Prize tick. What's next?
For me?
Yes.
Now I'm going around and giving lectures. I try to talk actually to many different people, especially to the young generation. This I found very, very interesting. The people and students.
Yeah. Well, you were giving a lecture to your students when you were told that you'd won, right?
Yes.
And you told the Nobel Committee to hang on a tick because you had a lecture.
Yeah. Yes.
Priorities.
Yes.
Stefan, what about you? Any more waves in your future?
Well, waves are in many of our futures, I think, because waves are symbols and substances of sea level rise. And I've become really interested in some peculiar things that are happening on the planet right now, which is that as climate changes and storm tracks change, waves, in fact, are getting taller than they used to be. And so the wave is kind of a symbol as well as an instantiation of the future coming toward us. And I think that's, and the sort of, I know that the geologists have just disqualified the Anthropocene as a...
I don't think they disqualified it. They got together, they had a really bad-tempered argument. I don't know if there's any of them in. And no one could agree about when... Does everyone know what the Anthropocene is? It's that epoch that, are we now in it, where we've put our dirty little fingers on everything in the planet?
And so waves are kind of figures of the Anthropocene coming at us from the ocean. So I'm really interested in the question of sea level rise and the question of increasing wave heights, and increasingly what kinds of mitigation strategies might be used. And some of them are really interesting. Instead of building seawalls, there's much more flexible infrastructure that people are trying to build, like maybe oyster beds or maybe more flexible kinds of mesh infrastructure around coastal cities. And so I want to keep an eye on that, on what we're going to do when the waves keep talking to us.
Right. Well, if you want Stefan to keep talking to you, same time tomorrow, 5 p.m. tomorrow, he's here, and it's free, like more than 200 activities this week. That's pretty much it for the opening ceremony. Thank you so much for turning up, and thank you so much to both of my guests. I want one final time your sound waves in clapping form for our speakers Stefan Helmreich and Nobel laureate Professor Anne Louis. So artist Anne Todney is back on shortly, and Soapbox Science will be available in the foyer, but this concludes the opening of the 28th International Science Festival here in Gothenburg. Thank you and good night.